Hello, everybody. Welcome to the post-lunch session. So we will start with Martin Claassen, who will tell us about quantum geometry in non-equilibrium Moire materials and beyond. Martin.
Okay, thank you. Can you hear me okay? Fantastic. Okay, so first of all, of course, thanks very, very much to the organizers for organizing this wonderful workshop. So what I'll start out in this session will be following the very, very nice introduction we heard in the morning from Inal on topology and geometry and geometrical interpretations of topology. But from the perspective of trying to think about light-matter coupling in quantum materials. So thinking about how photons can couple to electrons in quantum materials, and in particular with an emphasis on recent tailored designer materials and twisted Moire heterostructures and beyond. So that pretty much sums up a little bit already the motivation of this talk, sort of two fields to bring together with two for one new aspect of how photons can interact with electrons. One motivation, of course, comes from non-equilibrium materials as a general field of trying to think about using light or other external stimuli to control quantum matter. And this, of course, has a rich history in terms of ultra-fast dynamics, where you think about experiments with very sharp and strong but short pump pulses, and then probing the response of the material on ultra-fast timescales, which can explore nonlinearities, but in principle also induce changes of the material's phase to proximal metastable phases, or even to interrogate the equilibrium ground state beyond what's usually useful. The other aspect is very much at the heart of this conference, concerns periodically driven quantum systems. So if you're envisioning a very wide pump envelope, then you can imagine inquiring about the joint state of electrons interacting with light. So the resulting transient states, if the electromagnetic field is classical, are flow K states that essentially encode the period average dynamics. And we've heard interesting consequences for thermalization and ergodicity that play a key role in understanding timescales in such driven systems. So I'll try and take these two aspects as a motivation for this talk. One, just as a quick overview of what this means from the materials perspective, is there's been a great deal of effort in trying to think about engineering single particle properties, ranging from band engineering, so thinking about using light to engineer electronic band structures, to changing topological invariants, as we've heard in the morning, to changing emergent quasi-particles or excitons in semiconductors. And by now, there's already a range of experiments now that are addressing this from various angles, with pioneering experiments of thinking about flow K Dirac fermions and dynamical symmetry breaking, light-induced anomalous Hall effects, which we heard about last week, and more recently, new materials and new avenues for engineering single particle properties. However, the many body realm is, of course, a lot less rich in terms of experiments, but much richer in terms of proposed phenomenology, which can range from using light to engineer magnetism to more exotic states, such as fractional quantum Hall phases, or even changing pairing glues and superconductivities. One example is recently from David Che's group, ENCODE describes flow K engineering of optical nonlinearities, which is really a really beautiful manifestation of trying to dress atomic multiplets using very strong light fields in an interacting quantum material, and then probing ramifications for optical responses. Now, on the theory side, of course, the field is very rich, and there have been numerous proposals for engineering correlated states of matter, both using classical light fields, and actually it's not on this slide, but more recently also, and also in our group, thinking about cavity quantum materials and trying to interface weak photon pulses with strong electron-photon coupling in cavities. The other motivation, which is a very recent aspect in trying to understand correlated electron systems, comes from the appreciation that correlated electron systems really can be thought of as living on a spectrum of solids that range from conventional correlated electrons theories, such as the cuprates and nicolates. So let me illustrate what I mean by this. This is an example of a copper-oxygen blane for say, lanthanum copper oxide. At low energies in the undoped compound, I'll be at half filling of, to good approximation, is a band that is solely composed of the d orbitals of copper. I have an electronic interaction that is much larger than the bandwidth, and expect and observe a Mott insulator and antiferromagnetism at low temperature. So from a theorist's perspective, the real space picture of such a model is a tight binding description in terms of very well localized funny orbitals that mainly have the d orbital character of cuprates, The resulting interactions are typically well screened, so I can think about an emergent low energy model in terms of a Hubbard interaction on a lattice, which gives me a standard theory for Mott insulators. However, recently new materials have come to the fore that really break with these traditional paradigms, most prominently Moire heterostructures such as twisted bilayer graphene or twisted bilayer tungsten diselenide. So these systems are on one hand fascinating because we can really tailor electronic properties and electronic phases by control of the heterostructure composition and the twist angle. But the low energy theories are a lot harder to understand. So a prominent example again is twisted bilayer graphene, which is actually closely linked to a fragile topological obstruction that also showed up in the talk in the morning. So TBG in a nutshell has a twisted band structure near the magic angle where approximately dispersionless bands form near charge neutrality. So if we zoom into this little regime here, which we can reach via which we can dope via gating, we get bands that have a bandwidth on the order of maybe less than 10 milli-electron volts separated from other bands. And of course, we'd imagine, well, if we put our chemical potential into this band, we should envision that the low energy physics, presuming that interactions are not tremendously large in the Moire itself, should be governed solely by correlated electrons in these bands. But in the real space picture, it turns out that actually the Vanni orbitals, precisely because of topological origin, are poorly localized. We can still form localized Vanni orbitals using a little bit of legwork, but the resulting interacting theories at low energies are very far from the usual Hubbard theories that we're very comfortable with and have spent a great deal in addressing analytically and numerically. For instance, TBG at a minimum, and I will get into this in a lot more detail later, can be thought of as a plaquette interaction model of interactions on honeycomb lattice plaquettes that form in the twisted Moire supercell. Now, of course, the extreme limit on this scale is topological states, prominently fractional quantum Hall states, and more recently fractional Chern insulators, such as the very exciting recent experiments in twisted molybdenum ditelluride bilayers. So here, really, our bands can be thought as being analogous to Landau levels, almost dispersion or maybe perfectly dispersionless bands separated by a cyclotron spacing with a topological invariant, a non-zero Chern number. So here in real space, we have a proper topological obstruction to a local basis. There is no sense of a local description anymore if we constrain ourselves to the correlated electron problem in a single Landau level. And the resulting effective model in physics that we should expect is actually fascinating, but quite exotic, leading to fractional quantum Hall states, incompressible and compressible, fractional Chern insulators, and generally amount to projected interacting Landau level theories. So I should also say this work stands and interfaces two main collaborations, both at Penn and outside Penn. So in my group at Penn, we focus on quantum materials theory, low dimensional quantum materials, and in particular non-equilibrium dynamics, thinking about both ultra-fast materials control and more recent aspects such as cavity quantum materials or dissipative quantum systems in connection with Moire quantum materials, thinking about new routes to use, say, transition metal dichalcogenides, heterostructures to engineer new and designer quantum states in tailored heterostructures. But before I'll go to the gist of the talk, let me just briefly recap a little how we think about quantum geometry interfacing these two aspects and entering in a problem of coupling light to quantum matter. So if we think about an isolated atom, interaction with light is actually very straightforward. So we might imagine we have two isolated energy levels, say a ground energy level and an excited energy level. We might couple these two states with a photon. My transition matrix element will be a dipole transition given by an overlap matrix element with the dipole operator. Now, immediately, if I think about how this works in a solid, I'll now have electronic bands. And these bands will have a superposition of the original atomic orbitals that will change over the Brillouin zone. So if I demand an analogy to my dipole transition in the solid state setting, my interband transitions will now be governed by, instead of my atomic states, I'll now have Bloch wave functions, and my dipole transition matrix elements will be derivatives of the Bloch momentum. And this already tells you that there is a geometric ingredient in the coupling of light and matter. And in fact, quantum geometry really in a nutshell is essentially a geometric reinterpretation of the long wavelength structure of Bloch wave functions. So what that means is, imagine I take a Bloch state in the Brillouin zone at some Bloch momentum k. I can imagine parallel transport or an overlap between that Bloch state to a Bloch state in a small vicinity near the Bloch momentum K. So I'm transporting that momentum K to K plus a small infinitesimal shift delta in the Brillouin zone. If I think about the overlap matrix element of these Bloch states, I will get, in general, a phase factor and a change from unity, because the Bloch states might have slightly different orbital compositions. If I take delta to 0, I can parameterize these overlaps using a series of geometric quantities, prominently non-abelian generalizations of the Berry connection in multiband models, which take precisely the form that we already saw for the interband optical transitions, but also a quantum metric that characterizes the deviation from unity as I transport my Bloch state in a particular direction in the Brillouin zone, and gauge invariant quantities such as non-abelian Berry curvature that have recently attracted quite a bit of attention. So we need one more ingredient in order to get to the gist of the talk. So this is a momentum space description of quantum geometry, which of course is extremely fruitful and has garnered a lot of attention for studying optical responses of non-interacting electron systems. What we'll be interested in are going to be strongly correlated electron systems where the interaction energy scale is going to dominate over the electronic bandwidth. And interactions, at least well-screened interactions, typically will want, in many settings, want to localize charge carriers, or maybe do something more exotic. So the real space view of quantum geometry is actually very intuitive. So if I think of the real space analogy of my Bloch state, I have a Wannier function, which just amounts to, here's a simple example, which is actually a poor example for the purposes of what we're interested in, but imagine monolayer of tungsten diselenide. Here is a valence band composed of planar d orbitals. Imagine I were able to place my chemical potential into this band. I can devise an effective tight binding description by constructing a set of effective orbitals, Wannier orbitals, that are Fourier transforms with the Bloch states, and won't be perfectly localized anymore, but in general have some finite extent and a finite mixture of atomic orbitals that now form a triangular lattice description of the low energy structure. So if I had a chemical potential here and Coulomb interaction, and these bands are sufficiently far gapped, I should imagine all my both equilibrium physics and low frequency optical responses should be covered solely by the dynamics and of correlated electrons within this band using Wannier functions of this sort. Now, back to quantum geometry, the key ingredient is the extent of the Wannier orbital. A simple parametrization is just the Wannier spread, which is the mean squared deviation, which is bounded from below by Brillouin zone integrals of the Fubini-Studi metric. Again, tying this back in with our momentum space quantum geometric ingredients. And I'll keep in mind that there's, or we haven't said this yet, there's also a very, very nice derivation of a beautiful bound between the quantum metric and the Berry curvature, which tells us that this quantity is bounded from below by Brillouin zone integral of the Berry curvature, immediately telling us that, for instance, topological bands, correlated states in topological bands will generally have poorly localized or delocalized Wannier functions. Well, we'll focus for the main part of the talk on maximally localized Wannier functions, which is to say these are Wannier functions that have a tail that is exponentially localized, but might still have a finite extent in real space. But we can discuss generalizations to truly topological bands in which one cannot form a maximally localized Wannier function at all. Now, aspects of quantum geometry and optical responses in quantum materials have garnered a lot of interest, particularly in the field of free electrons. This is just a very hand-waving summary of various ingredients and responses that have been discovered. Of course, prominently Hall effects, such as the quantum Hall or quantum spin Hall effects. In terms of optical responses, photogalvanic effects and shift currents, which have a nice quantum geometric interpretations, circular photogalvanic effects, which can even give quantized responses in certain limits of topological semi-metals, and very recently generalizations to resonant optical responses in terms of various higher order quantum geometric ingredients. And I should state that this is a very incomplete list. So there is much more work on this topic on understanding free electron optical interactions and optical responses from quantum geometric ingredients. In contrast, in correlated electron systems, their list is rather short. So there's been quite a bit of work on fractional quantum Hall analogs on the lattice, such as fractional churn insulators, more recently excitons, and thinking about modifications of exciton energy levels and line shapes from quantum geometric ingredients. And very recently, there's been tremendous interest in trying to understand flat band superfluid weight, which is really, again, motivated by twisted bilayer graphene and the observed superconductivity. If you have a perfectly flat band, you would imagine that the superfluid weight should go to 0 because the electrons essentially don't move. There's no kinetics. It turns out that quantum geometry is a way out of this problem, which can be inferred from the real space picture we had on the previous slide. If there's a finite extent for my orbitals, correlated hopping from the finite necessary extent for Coulomb scattering can still induce a finite superfluid weight in a flat band. And this has been linked to, at least on the level of mean field theory, to the Fukini's 2D metric. Now, of course, topology and geometry in Moire materials is not constrained to twisted bilayer graphene. There's now a plethora of different materials platforms which have all the similar necessary ingredients for what we'll try to look at. For instance, twisted bilayer tungsten diselenide hosts twist controllable quantum spin Hall bands. Similarly, molybdenum ditelluride tungsten diselenide heterobilayers have been shown to host a fascinating set of quantum spin Hall and quantum anomalous Hall phases. And theoretically, we have numerous other predictions, such as group 4 TMDs or anisotropic Moire systems. I won't get into too much detail on this. We'll focus mainly on twisted bilayer graphene, but these considerations are in principle valid for any Moire material which will not be able to form perfectly well localized Fourier functions for its low energy bands. Now, why are Moire materials interesting for periodic driving in the context of this conference? Well, the simplest effect we can get from Fouquet physics in a solid is dynamical localization. If I imagine I just have a chain and electrons can hop along the chain, if I couple light in a very naive Peierls substitution coupling, my hoppings for electrons acquire a Peierls phase, which essentially oscillates periodically in time and is parametrized by a Fouquet parameter that scales with the electric field and the lattice constant. And so now if I think about going through a period in momentum space, is really just amounts taking the original dispersion and shifting it periodically through the Brillouin zone. So if I look at a single point, say here the gamma point, and period average over the location of the electronic dispersion, then the period average dispersion, you can convince yourself that the period average bandwidth is actually increased because average over a period, this will form a compromise of its extrema. So one might immediately infer, well, Moire materials seem to be pretty great to study, to observe this, because now the relevant Fouquet parameter scales with the lattice constant. The lattice constant in Moire systems can be nanometers. But it turns out that coupling to light in these systems is not as easy as a Peierls substitution. And it is really one of the premises of the talk to try and think how does light microscopically couple to Moire systems? And what is the missing ingredient beyond a simple Peierls in a Moire system? Now, this is actually a very long-standing story, and in fact is deeply tied to problems of gauge invariance in light-matter coupling. So a simple example is shown here. Imagine I have a band structure where I have a few bands near the Fermi energy, and they're gapped from higher energy bands here with some large band gap. And I'm interested in low frequency properties. Okay, say this might be detuned from this interband transition, such that I should expect all my response properties should be governed by correlated states that form in these bands. Right, so then intuitively what I should guess is, okay, I say I have strong Coulomb interactions, I might form a Mott insulator in these bands, and really my response should just come from these low energy bands, which then gives me, say, an optical conductivity that is governed here only by the Mott insulator and interband excitations being far, far at higher energy. Now, effective models of light-matter coupling, however, are much more challenging. So while the bare theory of minimal substitution in the theory of everything in a solid is, of course, very well understood, trying to come up with an effective theory of coupling light only to a small manifold of states in a correlated electron systems is very challenging. On the other hand, if you solve this challenge, you now have a straightforward interpretation of low frequency optical conductivity, second harmonic generations, or even, for the purposes of our talk, strong driving and non-equilibrium control. Just as a quick literature recap, to just in a very incomplete survey of the tremendous amount of work that has gone into this, mainly in the context of free electron optical responses. There's been much work in trying to formulate consistent descriptions of nonlinear optical responses, both phenomenologically and ab initio, as well as tackling the problem of gauge invariance in low energy manifolds by benchmarking or including ad hoc corrections in various gauge choices. And more recently, extensions to doing the Swiss quantized photons in cavities, which of course have the same challenges. So from a theorist point of view, where do these problems come up? This is going to inform our problem is actually very simple. Imagine I have a band structure like this. I have low energy bands here. My chemical potential lies in these bands. I'm far detuned from this band. I come in with a low frequency field. Should expect that all my responses are governed by electrons in these bands, and interband transitions must be suppressed by 1 over the detuning. So as a theorist, of course, I can just pretend that, let me take my band gap to infinity to have an exact limit for getting solely low frequency optical responses from these bands. Right? If I take the band gap to infinity, my dynamics should rigorously only depend on electron dynamics in these bands. But this is not quite so simple, because if you take a slightly closer look at the interband current, so we'll work in a velocity gauge description without loss of generality. If I look at an interband current matrix element between two bands, there's actually an old work from the 60s from Blount that shows that the interband current matrix element scales can be rewritten to scale as the band gap times an interband barrier connection as our first inkling of a quantum geometric ingredient. And that's, of course, immediately problematic, right? Because now let me do this theorist's picture of taking the band gap to higher energy inert bands to infinity. Well, there's two ways that I can do this. Either I have essentially trivial bands that inherit only the orbital character from individual atomic orbitals. Then I can safely take that band gap to infinity, which immediately decreases the hybridization between these bands and thereby decreasing the barrier connection, such that my interband current matrix element remains well defined. But there's another limit, in a sense, an band inverted or a topological limit, in which I insist on keeping the barrier connection constant, right? And insist on keeping an inverted orbital character, in which case we immediately see that the interband current operator scales with the band gap. And that's not good, right? So that's already not good in free electron descriptions. And becomes extremely problematic in correlated electron systems. So we'll need to find a cure for this. Just to show the problem, now imagine I have two bands and I come in with a highly off-resonant field. Here's my chemical potential again. I can envision a virtual process where I excite an electron from the valence band to the conduction band. This is way detuned, right? So I get a detuning, 1 over detuning factor, intermediate energy factor in my denominator for the effective matrix element. But then this virtual absorption process can be followed by an interband Coulomb scattering process where the photoexcited electron scatters off another electron in the valence band, leaving 2 electron hole pairs behind near the Fermi energy. The overall matrix element now scales as band gap over detuning times barrier connection times interaction. And we immediately see that even if this band gap is really, really large, the detuning is really large, this matrix element will be order 1. Okay. And so just for those of you who love diagrams, if you think about something, say, even linear optical, it even shows up in linear optical response. Ordinarily, optical conductivity would just be this fully dressed bubble. But now what this tells us that in general, in a multiband system with non-trivial quantum geometry, we have to also account for much more challenging processes that essentially encode these second order Coulomb-assisted interband transitions. Now, the root cause of this problem is that we've insisted on working with the equilibrium Bloch band basis to address our optical response or driving properties. And that can't be correct. So because physically we should not expect that high energy degrees of freedom contribute to a low energy response if we come in with low frequency photons. So, but this already immediately informs a cure, which just tells us that, well, we have to deform the basis somehow. Can we deform the equilibrium Bloch basis in a way to cancel these divergent interband contributions? And it turns out that there is a unique prescription that amounts to essentially deforming the original Bloch states or the original Wannier functions via a new quantum geometric ingredient that is a parallel transport factor. I'll motivate this in a second, but the gist of picking this deformation is to precisely cancel these divergent off-resonant interband transitions to get a well-defined low energy theory of correlated electrons coupled to low frequency light. So a way to understand this correction is actually, well, in equilibrium, again, adhering to this Bloch state Brillouin zone picture, I would pick my equilibrium basis to just be, say, a Bloch state at momentum K. K, of course, is a gauge-dependent momentum. And this Bloch state in real space gives me hopefully, if I gauged my Bloch state correctly, a maximally localized Wannier function. But now if I couple this to light, what I should really consider instead of the equilibrium Bloch state, I should pick the Bloch state at the gauge invariant momentum, k plus a, and then dress that Bloch state via a parallel transport factor that uses the non-abelian Berry connections of the low energy band to parallel transport back from the gauge invariant momentum to the gauge dependent momentum. And in momentum space, this just amounts to a non-abelian phase in the space of Bloch functions that span the bands near the Fermi energy. But if I Fourier transform this to get a Wannier function, if I change my phases of my Bloch function, I will change the shape and center of my Wannier functions. So what really happens, what you should envision is now the photon comes in, and in addition to coupling to electron kinetics, what the photon will now do for a Wannier orbital that is not perfectly localized, it'll start to deform the Wannier orbital. The effective electronic orbitals will oscillate in the electromagnetic field. And these oscillations, at least ignoring dynamical screening corrections, are solely governed by the quantum geometry. So another way, or a more theoretical way of stating this, is that really, if we talk about solids, we have two gauge choices that we have to do. There's a gauge choice for the electromagnetic field and for the Bloch-Wannier states. And these two gauge choices are not independent. So what this means on the level of effective theories for correlated electrons, so this is just writing down the correlated electrons problem in all generality for a subset of bands near the Fermi energy. The first term in the red box is just my ordinary kinetics, which is electrons hopping on a lattice, dressed, so I'm picking a velocity gauge without loss of generality. We could also work in a dipole gauge. I get a Peierls phase factor, as I should, but my hopping matrix elements are now also time dependent. So for the abuse of notation, t here is time and t here is hopping. And that time dependence comes straightforwardly from the deformation of the Wannier orbitals in the light field. Well, if the Wannier orbitals oscillate in the light field, my hopping matrix elements must also oscillate. But more importantly, it turns out that this effect also enters for two-particle Coulomb scattering, which now also get a Peierls phase as soon as it's not a purely local density-density interaction. But more importantly, the Coulomb matrix element is also time dependent, because what is this? This is nothing else than overlap matrix elements of my Wannier functions with a screened Coulomb interaction vertex at low energies. So we can write this out, and really, I would argue that this is a generic correction for quantum materials, but it's going to be very, very small in something like a cuprate, where the effective orbitals that compose a single band Hubbard model are really, really, really well localized, and essentially atomic in character. But these terms can actually dominate optical driving and responses in systems with non-trivial quantum geometry, prominently certain Moire heterostructures. And diagrammatically, this amounts to thinking, if I think about response properties, this amounts to now having to deal not only effectively with my usual paramagnetic, diamagnetic, and high order current vertices, but now also with two-particle current vertices that enter at all orders in nonlinear responses. So let me quickly, before I jump to Moire materials, let me give a very simple ramification in a toy model that is easy to analyze numerically. So the simplest model with an atomic Wannier obstruction that we can construct is can be formulated in 1 dimensions. So in 1D, we cannot have a true power law delocalized Wannier functions. All our Wannier functions are going to be exponentially localized, but we can nevertheless define simple multiband models in which that spread of the Wannier function can actually be relatively large. Simplest example here is a two orbital chain that is essentially a version of the SSH model. I have 2 orbitals per site coupled with a strong Hubbard interaction. Let me ignore spin degrees of freedom and hopping processes between these bands. This model is extremely nice because it has, first, it has a topological transition of SSH type, Z2, with a C2 invariant. It has a tunable dispersion as a function of the hopping parameters with an exact limit of a flat band. And it has an independently tunable spread of the Wannier function. So I can independently tune the dispersion of the lower band and the spread of the Wannier functions. And for our purposes, we'll again be interested in this, right? We'll put the chemical potential in the lower band at strong Coulomb interactions and inquire about optical responses of the many body state. Yeah, this is just a depiction of the Wannier spread as a function of tuning parameters. Now, the ground state of the system is extremely simple. In the limiting case where the lower band becomes flat, we can actually solve this analytically. the ground state, at least at half filling in that flat band, forms a bond density wave, where in the topological phase of the system, the Vanni orbitals are localized on bonds in the one-dimensional chain. And these bond localized centered orbitals are going to be filled, unfilled, even odd, filled, unfilled, forming a bond density wave ground state. Now, if I think about optical response properties, what I'll want to do is I want to drive this with low frequency light below the band gap and classify let's just look at linear optical response for simplicity, characterize the linear optical response as a function of the Vanni spread of this band. So this is just a quick check that we're doing everything correct. So this is again this theorist's toy idea of, let me change the band gap to infinity. As I do, my low frequency exact optical line shape, the corrections are just going to be 1 over the band gap. So that's not so exciting. The more exciting part is actually where does geometry enter now in the response? Well, what are my low energy excitations of that domain wall ground state? They're of that bond density wave ground state. There are going to be domain wall excitations. Domain wall excitations where I have 2 filled bond localized orbitals next to each other, forming a domain wall here, and similarly 2 unfilled forming a domain wall here. These domain walls in a flat band are completely static if the Vanni function were local. So as a function of delocalization of the Vanni function or the quantum geometry of the band, I can now induce domain wall dynamics from 2 particle scattering such that this domain wall can move. And this is immediately reflected in the optical response. So now I can look at optical conductivity calculation using the projected time-dependent Vanni function basis and find that, well, I get a well-defined domain wall mode that has now 2 features. So this is apologies, this is an exact diagonalization calculation. Hence the spikiness. You should really expect this to be a continuous mode that's observed in the thermodynamic limit. There's 2 features. The strength of the response increases with increasing Vanni spread, which is just to say that my coupling is sensitive to the quantum geometry of the band. If I make my Vanni spread wider, the Vanni function can couple more efficiently to light. And the spread of the mode also changes with increasing Vanni spread, just because my domain wall can move more efficiently. Okay, but now let me, in the remaining 8 minutes, is that with questions?
8 minutes with questions.
Okay, so then in the remaining few minutes, let me get to the prime application. So twisted bilayer graphene. Again, low energy bands near charge neutrality, almost flat. However, it's relatively challenging to construct localized effective Vanni orbitals and tight binding models for these flat, quasi-flat bands. Due to a fragile topological obstruction, one popular scheme for getting Vanni functions that are still exponentially localized at long distances amount to placing Vanni centers on the AB or BA stacking regions in the Moire unit cell. But the charge in TBG is localized in the AA stacking regions, which means that the Vanni functions now form this nice fidget spinner shape. The center sits on an AB region, but the charge is delocalized between the 3 neighboring AA regions. Yeah, and this is, of course, really neat, but also really challenging to understand on the level of many body physics. In particular, we should now expect that the low energy physics won't be simple Mott-Hubbard-like, but at minimum, we'd have to consider so-called plaquette-Coulomb interactions that include a plaquette charging term as well as correlated hopping terms around the plaquette, which just come from non-vanishing overlap matrix elements of these fidget spinners with joint AA sites. The phase diagram is extremely rich, but still quite contested. So these are just 2 examples of large-scale numerical calculations. This is quantum Monte Carlo at charge neutrality and DMRG at 3/4 filling. Charge neutrality shows a rich phase diagram of quantum Wily Hall inter-valley coherent states as a function of the competing interactions of the system, which are the charging terms versus the correlated hopping terms. The 3/4 state is better understood and is in terms of an experimentally observed quantum anomalous Hall state that can be understood to arise from predominantly correlated hopping interactions. Now, without further ado, what happens to these Vanni functions and driving? So here is the time-dependent Vanni functions with linearly polarized light with the quantum geometric correction, where the light field now deforms my Vanni functions periodically in the field. And similarly, circularly polarized driving for the 2 Vanni functions localized on the 2 AB and BA stacking sites. This is for reasonably, this is for terahertz fields and reasonably low intensities. What we'll envision in terms of control is we'll want to drive into the transparency gap of twisted bilayer graphene, and then inquire about how we can control materials parameters. Here we go. Okay, so where does this parameter modification come from? This is easily seen. For instance, here's a simple animation of an overlap matrix element. So these are two neighboring Wannier orbitals around a central AA site. And now, of course, my hopping matrix elements, but also Coulomb interactions, will be overlap matrix elements of these Wannier functions, which now vary in time. So both for linear and circular polarization, I will now find that my hopping amplitude will oscillate as a function of time and as a function of field strength. And similarly, I'll have a phase that is now a composition of Peierls phase and a phase from the chirality of the overlap matrix elements. But more interestingly, now if I think about electronic interactions, my Coulomb interactions will also change in time. And we'll see that already for relatively weak intensities, such as, what is this, 35, 40 kilovolts per centimeter at 2.4 terahertz. We'll find a transient renormalization of the equilibrium Coulomb interaction up to 50%, which is actually quite substantial for weak fields. So what does that mean for in terms of control of correlated phases? Since this is a workshop on periodically driven matter, let me just give you an aspect from flow K theory. So if I think again and go back to the picture of dynamical localization, we can now compute what is the flow K renormalized hopping amplitude. And this is depicted here in terms of the colored lines, with the dashed line being the naive expectation if I just do the simple lattice Peierls substitution that I showed a couple slides back. And it turns out that on the level of kinetics, in fact, the effective bandwidth in TBG is dominated by the Peierls phase. So nothing terribly exciting. The really interesting thing that comes is actually the control now of Coulomb interactions, which can govern the correlated phase. And again, if I constrain myself to these plaquette Coulomb interactions, on the level of flow K renormalization, I can get to reductions of the effective Coulomb interaction with respect to its equilibrium value to up to 50% at around 50 kilovolts per centimeter, again at 2.4 terahertz. More interestingly though, right, so I have two competing ingredients. I have an overall Coulomb interaction energy scale, and I have a competing correlated hopping term that can drive a phase transition. And this guy now varies dramatically under the drive, precisely because of that deformation of the Wannier orbital, giving me a handle to steer through the correlated phase diagram of twisted bilayer. So I'm almost out of time, so just quick ramifications that we're working on now. So there's various ramifications for optical responses. Already on the level of optical conductivity, if I take a Mott insulator in a system with non-trivial quantum geometry where my local moments won't be perfectly localized, I can now have an effective electric field coupling of terahertz fields to magnetic excitations just from the deformation of the effective shape of the local moments or Wannier functions that local host spins, coupling to spin exchange processes. More interestingly, I can think about things such as photogalvanic responses, where ordinarily, so these are responses in polar systems with broken inversion symmetry. I can inquire how would that look like in a strongly correlated electron system, such as a Mott insulator or a charge transfer insulator. In an inversion symmetry broken charge transfer insulator, naively, I would expect that my photogalvanic response will be dominated by charge transfer excitations from the ligand to the strongly interacting transition metal. But this now suggests there's a very different regime that can, for instance, be relative to Moire materials, where my bands are highly admixed and the dominant response comes from an anisotropic orbital deformation under the light field. And finally, we can also extend this formalism to strongly correlated, to strong topological invariance and correlated states in strong topological bands. Okay, so I think I'm pretty much out of time. Thanks for your attention. I'll leave the summary slide up and open up for questions.
Let's questions.
Can you make it more strongly correlated by driving? It seemed like you always decreased.
Yeah, so we have to define what we mean by strongly correlated. It seems like the Coulomb interaction in general decreases, but you can drive your way to a phase transition. So.
Any other?
The 1D SSH-like model you discussed with the two bands, are there experimental realizations which you have in mind or which have been published already?
No, nothing published yet. One possible realization are certain one-dimensional, again, let me go from the perspective of Moire heterostructures. If you take rectangular lattice van der Waals materials and twist them in, say, twisted bilayers, you will form effectively one-dimensional low-energy models that have the requisite physics that you need here. So you'll get.
And can you comment on the network, the tight binding network details in this model?
In the SSH-like model?
Yeah.
Yep. Let me just go back briefly. Yeah. So at low energies, I'm only going to be interested in one band that is going to be partially filled. And in this case, the hopping range is just going to be governed by the dispersion. So it doesn't really care about the Wannier extent. However, the Wannier extent enters in the Coulomb in the projected Coulomb interaction. So my effective Coulomb interactions can actually be very long ranged, even though I had an a priori well-screened Coulomb interaction.
Okay, but in the absence of interactions, what are...
Right, in the absence of interactions, actually the flat band limit is completely trivial.
Okay.
Because the charge can.
Okay, thank you.
Okay, so I don't see any other questions. Let's thank the speaker. Okay, so the next talk will be given by Shubhajit Sarkar, and he will tell us about quantum transport and discrete time crystals. So, Shubhajit, yes.
So thank you, and I'm happy to be here. Thanks for inviting me to present our work on quantum transport and discrete time crystals. This work I did with Yoni Dubey in Ben-Gurion University, and the work will be based on these two papers. So as I'm talking about discrete time crystals, first let me give a layman view of what is discrete time crystals. So these are periodically driven quantum many-body systems which has subharmonic response. These subharmonic response are indefinitely stable and robust against perturbation. So if I drive the system with some period t, the response should have a period which is more than t. And one criteria to look for if there is a subharmonic response is to look for the autocorrelation which are initially normalized. And regarding the robustness against perturbation, it depends on what kind of perturbation I am giving. So with that, so let me emphasize that this is a defining character of one of the most important defining character of discrete time crystals. And what I'm going to convey you that in a simple message that in a transport setup, current through electrodes can show the signatures of discrete time crystals. So by transport setup, what I mean is that I have a bunch of lattice sites where each site is being driven periodically with some period, and then I connect that system with two reservoirs. So from the left reservoir, I just inject particle, and from right reservoir, I extract it. And I complete the circuit and I see current through the circuit. And then from that current, I can directly infer that, okay, I have a DTC. So to motivate, so let me first go through some selected experiments just to show you how there are several experiments just to show you the paradigms of discrete time crystals. So if in a closed system, one paradigm is if you have a many-body localized phase, then you have a discrete time crystal, and there is a subharmonic frequency and period doubling. So here the blue line, it corresponds to the MBL phase, and the system is a chain of carbon atoms near an NV center. So now if you are moving away from many body localized states, your time crystal will decay, and far away it will have multiple frequencies. So there is another paradigm which is called pre-thermal discrete time crystals, where you have a long-range interacting system, such as an ion traps quantum simulator, and you drive the system really fast, like very high frequency. And in this way, you just separate out a few time scales, like one is a thermalization time scale, one another is a pre-thermalization time scale. So in between that, you have a sustained oscillation, and the oscillation will eventually decay, but the decay time will increase as you increase the driving frequency. It's actually what is happening, as far as I understand, is that the system is not following the driving frequency, and that's why you have this pre-thermalization. But these are all the story in the closed system. So the point is, in closed system, if you continuously drive a system, you generate heat, and your system will eventually heat up to zero oscillation. So to counter these pre-thermal and MBL phase, MBL time crystal has been proposed. The point is that one just hinders or delay the thermalization, and another is just stops the energy from spreading across the system. Now, another aspect is open system. Here, if you give energy to the system, since your system is open, it just dissipates to the environment. In that way, also you can stabilize a discrete time crystal. So this is an experiment where they have a cavity, they have a rubidium collection of rubidium atoms in a cavity, and they're pumping from outside, and they have this cavity field. Now, they prepare the system in a Bose-Einstein condensate, and above certain critical pumping field, they start having DEC to density wave transition. And once they have a density wave transition, they basically oscillate between two different type of density waves, like two different checkerboard patterns. Now, this is their driving protocol, and this is the time crystal oscillation. Now, here is an interesting feature. So the time crystal is seen between the relative phase, in the relative phase between pump and cavity field. Now, in their system, as long as they have a cavity field, finite cavity field, they have what is called a mean field character of the Hamiltonian or the system. So you can clearly see that as the cavity field decays, you lose the time crystal, although the amplitude of the oscillation remains, so you just lose the frequency. So this is a signature that once you go away from the mean field limit, you lose the time crystal in the frequency. A similar study has been done on a car nonlinear optical microcavity, and then they also find some similar thing. So my point in these slides is that the state of the art is only optical detection. So you just have optical means of looking at time crystals. And I asked that, what about transport? So let me find an analogy, the situation. So I have a bunch of kids. Kids are like quantum particles. So they are there and playing. And then they are locally creating some time crystals. Now, optical detection is something like this. You send up a drone and look at the drone footage and say, oh, haha, here is my TC. And I don't have the money to buy drone. I just do what? I regularly clean my pool. So I just add a smooth flow of water, and kids are still playing. They don't know there is a smooth flow of water. So the time crystal will propagate through, and the mom is sitting far away from the kids. She can just see and look at the flow and say, oh, I can see the kids are playing TC game. So this is the kind of analogy that I'm imagining. So to see this, so first I have to look at what to expect from the transport setup. So to do this, I just work in the Lindblad equation premise. So Lindblad equation says that I have a system inside some surroundings. The system's density matrix will evolve in time following this equation. This equation has a coherent part and a dissipator part. The dissipator part contains a collection of jump operators or Lindblad operators. These Lindblad operators encodes what the system, what the surrounding is doing with the system. So basically, for example, if I have a boundary drive like the electrodes or the leads I showed you, the leads will create particle to the system, and one end it will also extract particle from the system. So this is how it works. So in my case, I will work only with the Markovian limit and my Hamiltonian is periodic. Therefore, all the periodicity in my Lindblad or Liouvillean is coming from the Hamiltonian. In the operator form, the equation of motion looks like this. Now, this is what we'll be analyzing in the next slide. So now let's see what to look for if I want to have a time crystal. So I have a Liouvillean which is time periodic. What I will look at is one period time evolution map or Floquet map. This looks like a time ordered exponential of the Liouvillean superoperator. The superoperator means that I have a density matrix which has the dimension of the Hamiltonian. I just make the density matrix a vector and extend that the Liouvillean accordingly. And then for all the basis states, I time evolve the Liouvillean, I mean this thing to get after one period, one Floquet map or the time evolution map. Then I diagonalize it and plot the real and imaginary part of the one period Floquet map. So as you can see, there is one state which is at eigenvalue 1, all the rest of the states are decaying. This state is called Floquet state, Floquet steady state. And correspondingly, I don't have any phase over there. It's just 1 plus 0i. Now, what will happen if I have an underlying discrete time crystal? How do I see it? So if I now diagonalize a one period Floquet map, apart from this Floquet steady state, I see other states which appear on the unit circle, but having a phase. So the magnitude of the eigenvalue would be 1, but it will have a phase. Now they appear in pair. So here, the phase is like 2 pi over n. I mean, the n might not be integer, it might be fraction. If you have a fractional n, then you call it's a discrete time quasi-crystal. Now, the density matrix will have a nt periodicity, while the Liouvillean will have a t periodicity. And this is how I will diagnose a discrete time crystal from one period Floquet map. What is the mechanism by having a discrete time crystal? So I showed you the equation of motion for the operators. So my Hamiltonian is periodically driven. I have a dissipator. Then I try to find out a frame where Hamiltonian becomes effectively static. And if I find such a good way of having such a frame, then my equation of motion is time independent. By my right-hand part is time independent. And the mechanism is something called dynamical symmetry. This is a brainchild of Borislav, who is sitting there. So it says that Hamiltonian, and there is an operator called dynamical symmetry operator, which satisfy eigenoperator condition with the Hamiltonian, and the dissipator part is 0 for this particular operator. In that case, I will have a discrete time crystal seen in the dynamical symmetry operator. What is actually happening is that dissipator is separating the full Hilbert space into separate disjoint subsectors. So each subsector will oscillate with the frequency omega, and this dynamical symmetry operator will act as a dark Hamiltonian, which will induce some coherence between two different subsectors, and that coherence has a value of lambda, which will be seen as a response. So the role of the dissipator is to have this kind of a separation. So this dynamical symmetry is such a separation of Hilbert space or such kind of thing occurs like more generally in systems such as quantum many body scar and systems like that. And in that sense, it will be like something like an eigenoperator thermalization, which Borislav will talk about in his lectures. In my case, I want to now see what happens to the transport. So given I have such a mechanism of DTC, I don't want to send my drones. I just want to see it in transport, that means on the water flow. So I add leads, and the kind of systems I will imagine, I'll show you shortly, these leads are naturally there. They need that to implement their setup itself. So in that case, particles will flow in to the two different sectors and flow out. And while going out, it just captures the underlying coherence. So in that case, what we must have is that apart from the eigenoperator with respect to the Hamiltonian, I also need to have an eigenoperator with respect to dissipator. And this lambda and gamma, they should not depend on each other. And in that case, I'll have this decaying envelope, but the frequency will not be hampered, as I will show. And I will see oscillations in the current under this kind of a mechanism. So to show it, so let me show you the model and the setup. So I have a Fermi-Hubbard model. I drive it externally. I have a local Zeeman type circularly polarized drive. I have hopping of electrons from one side to another. I have on-site interaction. I have nearest neighbor interaction. And I also have something called spin agnostic dephasing. It means that it's measuring number of particles at a rate of square root of gamma, total number of upspin and downspin electrons at a rate square root of gamma at each side. Now I add electrodes. So from left, I inject, and from right, I only extract. So this is a condition corresponds to an infinite bias condition. Now with this model, let me now analyze the one period Floquet map for various values of gamma, my system lead coupling, and which is usually tunable. So here I plot for various values of gamma, the one period Floquet map, the way I explained you, the way I got it. Now, this is the real part and this is the imaginary part. And if I have a gamma equals to 0, that means no transport. I have this as my DTC eigenvalue. Now, if I start adding transport, I see that there is a real part coming in, and that real part is not, that real part has only effect to shift these time crystal eigenvalues along a ray. So importantly, we have omega equals to all other energy scales of the system. So the role of the system lead coupling is to shift the eigenvalues along a ray. And in this way, what we can see is that although the amplitude of the signal reduces with increasing system lead coupling, but the frequency remains intact. So this will help us seeing time crystals in the current. And how? So this is the kind of picture I have. So I'm plotting here spin current. Spin current is the difference between the upspin current and downspin current. So I think I forgot to mention the kind of setup I'm imagining is on a quantum dot array. So here in quantum dot array, we have naturally they implement these source and drain. So here I plot spin current as a function of time for say 100 driving periods. So if I have a weak system lead coupling, I see sustained oscillation, which is expected, and I have a frequency at 5/3 omega. Now, if I increase the system lead coupling, some intermediate values, I see the oscillation amplitude decays, but I still see a sustained oscillation in, say, these long time periods, long time scale. So here also I have the frequency 5/3 omega, but now I am increasing the system lead coupling to something like beyond, I expect, using Lindblad equation, such as like almost 1/50th of the frequency or the energy scales of the system. Here also I see the frequency remains there, but now we have lots of broadenings because of the amplitude decay. What is happening is that I get this frequency from two components. One is the amplitude, another is amplitude of the external drive, and another is the frequency of the external drive. And as you notice, the spin current provides a signature of the coherence between the system symmetry subsector, and it directly reflects the coherence, and the amplitude remains locked. And this is, I find, beneficial for looking at time crystal using transport. But you may argue that this is 5/3, so it's higher harmonics. It's not subharmonic. So let me now show you where actually the time crystal appears. The time crystal appears in SY. SY is so in my case, I'm working with Fermi-Hubbard model. In Fermi-Hubbard model, the dynamical symmetry operator is the total spin raising operator. So real or imaginary part of that total spin raising operator at any site will oscillate, and that will show me the time crystal. So although I'm getting a higher harmonics in the current, the time crystal appears in SY. As you can see, this is the SY for gamma equals to 10 power minus 5 omega. So the order of gammas are same as here and here. So this is the small gamma, and I have a frequency 2/3, which is the coherence modulo omega. So in my choice of parameter, it's a rational fraction. So I get a time DTC period, which is P times T. And if I increase the amplitude of the system lead coupling, and I get the same frequency, and then the entire feature remains the same. One thing worth noticing is that here I have a synchronization. So I plot 3 different sites, and all 3 sites are oscillating in synchronization, but they did not start with in synchronization. So the role of gamma is to bring, the gamma means the dephasing, is to bring the synchronization. And the role of a boundary drive is to drive a current through the system. Now let me connect why I have a 5/3 in the current and 2/3 in time crystal. So to connect that, I look at the Fourier transform, and I see there is a component at 2/3, there is a component at omega. So clearly, this combination is drawn here. These two matches with each other. This is my analytical form here, and this is what I get from numerics. As you can see, the SY has 5/3 omega and times sine of omega t. Similarly, I can have an SX, which also have a 5/3 omega component and omega t by 3. Now, given that for very small gamma, I must have this property to be constant. As you can see, the SZ oscillates, should oscillate with 5/3 omega. And this is what was happening here. Now, having said that, I showed you that I have to look for the spin currents. Now, looking at spin current is difficult in the sense I have to then tune my leads in a quantum dot setup to really filter up spin and down spin, and then look at the spin current. So let's implement the whole thing in a charge measurable setup. So the symmetry, underlying symmetry in my Hamiltonian is SU2. So I want to implement the SU2 symmetric system in a array kind of structure. So now here is my imagination. So I have a chain of dots. Each dot contains spinless fermions, and their energy levels can be changed by some gate thing. And then electrons can hop from one dot to another. They can have on-site and nearest neighbor interactions. One non-trivial thing to implement is the interchain hopping now needs to be periodic. So if I can implement this interchain hopping to be periodic, then my setup can show, given a periodic omega periodic drive, that 5/3 omega in current. Now this imagination is not far from reality, although I did not know it earlier. So recently I figured out that there is an experiment implementing SSH model on a quantum dot array setup. And as you can see, in their setup is architecture-wise quite similar to a ladder structure. And they also have a source drain. So only non-trivial part would be to have interchain hopping periodic and to implement the spin agnostic, in this case, this chain-wise, ladder-wise dephasing. So if that can be implemented, then the discrete time crystal is seen in charge current. So I drive the system and I see charge current oscillating in time, giving me a 5/3 omega frequency. And this time I don't need to separate out upspin and downspin contributions. But the underlying DTC is actually in a different operator. That operator is the interchain tunneling operator. Either real part or imaginary part will show these 2/3 omega oscillations. So therefore, so now the bottom line is that charge current shows discrete time crystal behavior. Now, one more thing we can do with this kind of a ladder setup is that we can use gates to increase or decrease the on-site energy. So there is another tuning parameter, which is the on-site energies. So depending on the difference of on-site energies, I can now tune between time crystal and a Floquet response. Now, question is it really a Floquet response, or is it really a Floquet steady state? That's what I am going to answer now. So when my delta epsilon is 0 or some value that gives me lambda by omega as a rational fraction, I get a DTC response. And at a value when delta omega is exactly equals to the magnitude of the hopping, interchain hopping, this hopping, then I get lambda by omega as an integer. That means my this DTC period is actually exactly same as the Floquet response. Now if I deviate from this point, I again start seeing subharmonic response. So actually what is happening, you can see it in current. I start from a lambda where delta epsilon, where I have DTC response, I change. So it's seen in the current. And as you can see, it's seen in the Fourier transform. So now once I change it to a value, which is like equal to the T hopping, interchain hopping, you can see now I have a response, which is Floquet response. Now, if I change it back, I get back to the DTC response once again. What is happening here? A DTC state is moving along the unit circle, and it just becomes degenerate with the Floquet steady state. And once I change the parameter again, it starts moving. So it's just a degenerate, but the DTC state is really orthogonal to the Floquet steady state. So I was expecting that once it goes there, it will remain there, but it's not actually because of the orthogonality between them. So with this, so let me now summarize. What I showed you is that there can be an electrically tunable quantum dot array setup where we can implement a way to measure time crystal in current, and we can have both in spin polarized and charge current, and the amplitude decays, but the frequency remains same. This is due to our weak local Floquet dynamical symmetry, and I forgot to mention why it is weak and local. So the weak because your amplitude is decaying, and local because you are now having the dynamical symmetry not with the extensive spin operator, but the operators that are situated on the left, near the left and the right lead. This is why we named it a weak local Floquet dynamical symmetry operator. So basically, what it does is that it adds an extra eigenoperator condition on top of the eigenoperator condition you have had in the Hamiltonian. And robust, this is robust against quenching of the system parameters. This I end.
Thank you. Let's thank the speaker. Questions?
Floquet map diagram, you might have a finite number of spins, right? And you are studying it as a the decay rate dependence on the real part of the eigenvalues, right?
Yes.
What is the effect of the system size scaling on that?
There is no effect on the system size scaling, because this is analytical. This is just a representative kind of to support the analytics. It's analytically provable.
So if I take like a finite
Yes.
number of spins, like 2 or 3 spins, that
Yes,
will
yes.
still exist?
Yes, yes.
Okay, correct me if I'm wrong, because like I think the many body correlation stabilize this discrete time crystals phases, right?
This discrete time crystal is stabilized by the dephasing. Actually, your dephasing creates a disjoint subsectors, and that's where the discrete time crystal is coming.
And one more question on that is that when you have local dephasing, can you still conserve the total spin that I think you have shown on one of the
So the
slides?
dephasing has to be spin agnostic. That means it has to be an up plus and down. Otherwise, you cannot.
I think
This dephasing conserve the conserve the
Okay.
number, particle number.
okay. Yeah.
Okay. Abhishek, the question.
It's a very basic question. I mean, so this 2 extra eigenvalues that you get, does this happen in the kind of thermodynamic limit, or it's finite?
Irrespective of taking thermodynamics.
It happens in a finite system.
It's just like it's an analytical condition. In order to show it through Floquet map, I had to consider finite size. But the condition, why is it coming, is because of Why is it coming is because of this equation. So if you make gamma 0, then you will always have this kind of a, irrespective of the system size. And even with gamma, it's just adding an extra decay, and this decay is actually helping me to see the current. With 0 gamma, I cannot have a current, right? So
No, but then why is it a crystal? Because crystals normally you think like it should be in the.
so analytically, it's just in the any n, like it's valid also in n tends to infinity limit. I just cannot have like a way to show it here. Like in order to have the entire spectrum, I have to have finite number of particles.
I guess the question is, suppose I just had one dot coupled to two bars.
There is no.
How many minimum dots would you need?
Two at least.
Two.
You need. And this was the question from the referee also.
Yeah. So you need two for the operator algebra to work.
Yes.
Any other questions? Yeah.
Yes.
That's basically the steady state, right? You must have it because there is a steady state
Yes.
somewhere. And then you say the oscillations come because there is like three, well, the time crystal, because there are 3 points that are somehow symmetric.
This doesn't have a phase, so it's kind of will follow the drive.
Yeah.
It will respond same as omega.
Right.
And this has an extra phase,
Right.
so you have to have that extra, that because of that extra phase, you get these extra periodics.
Right. So my question was, if I understood correctly the story, at least in the transverse shieldizing model, it is actually not just a property of one eigenvalue, but all eigenvalue will have, say, a pair exactly.
Yeah, there is a pair.
No, I mean, so I'm saying, let's take another dot. Will it also have a partner? Or is it only the
Yes,
steady
yes.
state that has a
It
partner?
depends. Okay, so this is this specific value is because of my parameter choice.
Yeah, no, I understand.
So-
But let's
so-
say you take a point in the middle, not on the edge of the spectrum, not the steady, not just in the middle, not any of those dots you have.
So you're saying they have a partner or not? I think yes. There are. I mean, is it like?
Yeah, that was the question. Yeah, if every point will have like 2 partners.
Kind of,
Or-
yes.
Yeah, you think so? Okay, thanks.
No, but then this point no. This point cannot have 2 partners, right? This is a unique state. Apart from that, like these, I guess all of them have partners. Because these has phase, so they come in pairs. But this doesn't have a phase. Question is what?
I just wanted to say, but I think it's clear, they must come in pairs because of hermeticity preservation of the map, yeah? This is guaranteed. I'm not beyond that now understood that you're asking something else, but
Any other questions? If not, let's thank the speaker.
Thank you.